Hello everyone. In this video we'll do a brief introduction to parametric equations. Alright, so what are parametric equations and what are they used for? So first let's just think about what equations we're used to seeing, right? We're usually used to seeing either explicit functions of x or sometimes we've seen implicit functions as well, right? So classic example being circle of radius r. So these xy coordinates, this is called the rectangular coordinate system or Cartesian coordinate system. And the reason for this is that our axes meet at right angles, and basically this means the variables are independent of each other. So you've probably noticed that graphing explicit functions y equals f of x has been a lot easier than dealing with implicitly defined functions. So parametric equations basically can make our lives easier when dealing with graphing things that aren't functions, right? Like the circle, like ellipses, like hyperbolas. They give us another way to think about these things. And one other thing that they're good at is for capturing like particle motion or something changing in space, whether it be in the plane or in 3D or more if you're into thinking about those things over time. So we'll talk about that more in a bit. So now we should actually define parametric equations, right? So we've talked about why they're useful, but what exactly are they? So we're used to, again, x and y coordinates. So what we're going to do is express both x and y as functions of what's called our parameter, which we'll usually call t. So you can, again, think of this as motion over time, where you have x as your motion in the horizontal direction and y is your vertical motion and t is time, right? So t is our parameter here, and these together form a parametric equation. So one of the first examples that we said that these are good for circles. So we want to express a circle this way. So let's do the unit circle. So it turns out we can write x is cosine t and y is sine t, and use t values between 0 and 2 pi, right? Just one full period around the unit circle. And so when we're graphing these things, we should graph for different values of t and then just look at what the x and y coordinates are going to be, right? So when t is 0, I've got cosine of 0, which is 1, sine of 0 is 0. At pi over 6, we have root 3 over 2, we have 1/2 for y. And now we can graph this in the xy plane. So we're just going to start at time 0, right? So we start at 1, 0. And then we have root 3 over 2, 1/2. Root 2 over 2, root 2 over 2. We go here, then we're up at 0, 1. And you can keep going. And the point is, you're going to end up getting, right, at pi, you would get -1, 0. You keep going around, and you end up getting the unit circle. And notice that since we're doing this over time, we can actually see a direction here, right? This is traveling counterclockwise around the unit circle exactly one time because we start at 0, and then we head back to 2 pi and stop. You could keep going, but this would just be making loops around this same circle. So something you might have wondered there is, are these different, right? So I said that x equals cosine of t, y equals sine of t, where t was between 0 and 2 pi was the same as the unit circle, but we're used to seeing the unit circle as x squared plus y squared equals 1. Well, is this true? Well, sure, right? So we can just plug in, we can substitute, and we get cosine squared t plus sine squared t, which cosine squared plus sine squared is 1, right? This is the Pythagorean identity. So you can see that these are definitely points on the circle of radius 1. The fact that we go all the way around from 0 to 2 pi means that we get the whole circle. So let's look at another example here. So let's look at x as 6 minus t squared, and y is 2t minus 4. So we're just going to fill in a table again. So in this case, I'm not given bounds on t, right? I'm not saying it's between 0 and 2 pi. So let's just start somewhere. Let's just start close to 0, and we'll just kind of move left to right in terms of time. So let's just plug in -2, -1, 0, 1, and 2, and see if we can figure out what's going on. Okay, so if we plug in -2, then we're going to get 6 minus 4, which is 2, and -4 minus 4, which is -8. Okay, if we keep going, 6 minus 1 is 5, -2, so this is -6, 0, we get 6, 1, back to 5, 2, right, so this is a parabola, and so we see that going up and then back down, and this is just a line of slope 2, so we're just going to go up 2 each time. Okay, so what actually happens? What does our graph look like? So again, we're not graphing t, right? So you want to look at these x values and think, okay, so I've got 1, 2, 3, 4, 5, 6. Well, I don't really need to go that way. 2, 3, 4, 5, 6, 7, 8. Okay, so we start at 2, -8. Then we go to 5, -6. 6, -4. 5, -2, and then 2, 0. And you can see what's going on, right? So again, we didn't have a lower bound, so we're coming in from this direction, and we see a parabola opening up to the left, right? And again, thinking about time, as t goes forward, we're going in this direction, right? So I mean, this looks like something like an x equals, ay squared plus by plus c. Can we figure out what that is? Can we figure out what parabola this is? So we do have a method for doing so. It's called eliminating the parameter. So basically, eliminate the parameter t, and then get everything in terms of x and y. So let's see how to do that. So when you're looking at these two things, if we want to get rid of t, we should solve for it. And that's going to be much easier to do in the second equation, right? Because it's linear. So we see that 2t is equal to y plus 4. And so t is equal to y plus 4 over 2. And therefore, plugging it in, we have x is equal to 6 minus y plus 4 over 2 squared. Right, and so this is your usual parabola here. Only in terms of x and y, right? And so we have eliminated the parameter there. So for your first exercise, I want you to give the parametric equation for the unit circle in the first, second, and third quadrants. So what I mean by that is a circle of radius 1 that goes here, and we don't finish it up. So think about why I'm asking this, right? So the parametric equation turns out not to be too bad here, but think about whether this would be very easy or not to do just in terms of x and y, right, if you use rectangular coordinates. All right, for your second exercise, I want you to go ahead and eliminate the parameter here and rewrite this as an explicit function y in terms of x.